Hey, hello there. So let's talk about this question 924, minimize malware spread. We have a network of nodes, maybe computer nodes. Each node I is directly connected to another node J if and only if graph ij is equal to 1. So we've been given this adjacency matrix representation for the graph. And I think this connection here is undirected. So it's if I is connecting to J, graph ij, this 2D array is going to equal to 1. And the graph ji is also going to be equal to 1. So it's symmetric. If you flip it around the diagonal, it will match perfectly. So that's the representation of the graph adjacency matrix. Some initial nodes, maybe a list of nodes, are infected by malware. Whenever two nodes are connected and one of the node has the malware, it will affect the other one. It will infect the other good machine. And this will spread until no more nodes can be infected. So in the end, maybe there are some nodes just isolated by themselves. They are not going to be infected. Otherwise, it will basically infect every computer in there. So suppose that we have this function m initial, which takes the set of nodes initially being infected by the malware, and maybe we run a simulation. In the end, until this converges, we count the number of nodes infected with the malware in the entire network. That's what this function returns. So giving an initial set of nodes with malware and run this spreading simulation and return the final count for the infected machines. So we want to do is to remove one of the initial infected nodes from the list, and we want to return the machine. If removed, it will minimize the m initial. So basically, if we run this with the initial set of nodes, we return the result is like a 50, maybe 50 machines affected. Let's say that we can remove one of the node being infected in the beginning. The final result may reduce to 45. So we minimize, we reduce 5. Maybe there is another node. If it's not initially affected in the final result, the total number being affected is going to be 40, then we definitely want to remove the latter one, because it will reduce this final count of infected machine more than the previous one. So we want to find a node that can reduce this as much as possible. And if there are ties, multiple nodes, if we remove that single node, can cause this to reduce to the same amount. We return the node with the smallest index. So yeah, if there are ties, we return the smallest index. So that's this question. If there so here is a final note. Here is that if there is a node was removed from the initial list, it may still be infected by later on as a result of malware spread. So yeah, so for this question, I'm gonna try to make some plots. My drawing is so bad, so I'm using tools. So let's say that we have a couple of nodes. If the nodes has a little star on top, that means it's initially being affected. Let's just say that we have a couple of this. Maybe this is node 0 initially being infected, 0, and we have another node 1 that's directly connected with this. So since it's an undirected graph, I'm gonna remove the arrow. Maybe we have another some other nodes, 2 and 3. Both of these nodes are initially affected, and maybe we have some more. 4 and 5. None of those nodes are infected. What I'm doing here is basically trying to have some nodes that connect to each other and with different number of initial infection there, and see if we remove one, which one should I remove. So just based on this example, if we let the malware spread with this initial is going to be, just put it here, 6 nodes, 3, and initial. I'm gonna enlarge this, so don't worry. Okay. So we have 6 nodes, and the initial is 0, 2, and 3. So just looking at that, if we let the malware spread, node 1 is going to be infected by node 0. So in the end, we will end up with m equal to 4. So which one we remove from the list? Obviously the answer is 0, because if we remove 0 from the initial infected one, it will become the latter case, like the 4 and 5 there. It's not going to be spreading. So if we remove 0 from the initial, we'll end up with m equal to 3. Yeah, so that's why we want to remove 0. What if that we remove 2? If we remove 2, m is actually unchanged, because if we remove 2 from the initial malware list, since that node 3 still have that malware, it will spread over to node 2. So we notice that what we want to do is to find a connected components with a single node that is not affected. If there are multiple nodes inside this connected components that's being affected by the malware in the beginning, in the initial list, in the end, even if you remove it from the initial affected list, it's going to be got it again. So what we want to do is to just going to note down here, back here, for find the connected component with only one initial infection. And since that, let's say if we have another connected component with node 6, 7, and 8, 3 nodes connected component, and only one node is initially infected. Choosing this, and this is making choice between 0, 1, this component, and 6, 7, 8, we definitely will go for the larger one. So because if we remove 6 from the initial infection list, then the m, it's going to reduce by 3 compared to the original initial effects. So just add one line here. So we do that. What we do is to first find the components with only one initial infection. Second is to find the largest amount above. And if there are tie, we choose the smaller index. And obviously, very first thing we can do is actually find all the connected components. So that's pretty much the strategy to solve this problem. Just looking at the graph and figure out what are the connected components, and within all the connected components, we want to find those components with only one nodes initially being infected. Because if we find other components with more than one, since we can only remove one, it's gonna come back again. So there's no effect whatsoever if we choose to remove one of the nodes from the initial list that's in a components with more than one initial infection. So we want to look at the components with only one component initially infected, and among all those, what we want to do is to compare which one has the largest size. And if there are multiple connected components with only one initial infection nodes of the same size, we want to return the nodes, infection nodes with the smallest index. So that's the procedure to solve this problem. So in terms of the time and space complexity, this is squared. And to find the connected component with only one initial infection, what we're going to do is just enumerate over the list of initial infections and find its connected component and add that count for that. So just count for every connected component, how many initial infected nodes are there. So if everything is by itself a connected component and everything is in the initial infection, this step is going to run in square time as well. But generally, that's going to be upper bounded by the number of nodes inside this initial. So I'm just going to put this here, and we need to find the largest amount above. So this is order of number of connected components. These things get smaller and smaller, so the total runtime is going to be upper bounded by square time. And this is just a finding, so it should be with this too, even less than this. So anyway, the upper bound time complexity, the largest item is the finding of all the connected components. So it's a square time algorithm. So for that, the data structure of choice is of course union find. It's been the topic for my whole weeks right now. So I'm just going to copy the union find code here and use this to find all the connected components to establish the first step, and then do some post-processing after we got all those. Yeah, so let's code this question up. Yeah, this time I don't need to modify this because we know the initial number of nodes, and this is perfectly fine. We are not doing any kind of a dynamic connection, so just use the template as this, as it is. So just grab the number of nodes here and initialize the data structure union find with this initial number. Then I'm just going to do the connected components. So I'm iterating over all the entries inside this adjacency matrix. If there is a connection, we do the union. So this is a nested loop which costs square time. We find the number of find all the connected components with also the sizing information in there. Then what we're gonna do is to iterate over the initial and try to annotate each connected component with the number of infection it has. Yeah, so I'm just gonna do for I in initial. For all the nodes inside this initial infected one, we're gonna create a mapping from the the cluster ID, the connected component ID, representative node ID to the number of infection there. So we need a hash map for that. Let's just call this infected in the beginning. So this is 0 in the beginning. Every component is infected by zero initial nodes. So what I'm going to do is just increment that. And for the infected nodes, I need to find its component representative. So that's uf.find I. I'm going to increment this by 1. So after this, I have a I'm able to tell that the components with only one initial infection. So what's left is to iterate over all those connected components with one initial infection and find the largest one among them. So So for this, I'm gonna have this to keep track of the maximum size of the connected component IC, and I'm also gonna basically drill down to the one. This 2 and 3 can actually be combined together. So let's just call this 2A, 2B. The candidate can initially be the minimum from the I don't know, maybe we deal with this later. So for I in initial, the reason that I'm doing this is if I do find I, it will be the yeah, because the components with 0 initial infection I don't really care about, so I don't need to go through them to find the largest with 1 count, a single initial infection node. So that's why I'm iterating over this instead of iterating over n. This can potentially be slightly smaller. Infection count is gonna be grabbing that from here. And the sizing information is something we get from UF. And we're just gonna check if this is not 1. We're gonna continue, skip this initial infected nodes. Because we don't care about this, because since that it has more than 1 nodes being initially infected, even if I move it from the initial, it will come back. So if it continues, that means this particular connected component has only that node as the initial infected node. We're gonna test the size. If it's larger than the maximum we've seen so far, we're gonna do some updates. And actually, I'm just gonna do a sort here. Since that this is potentially n log n, but we overshadowed by the n square, but the sort can make the code slightly better, cleaner. If we don't do sort, we have to test if the size is equal to the current maximum. Let's just do that. And this index is less than the previous candidate. We're gonna update only the candidate index. So for that reason, the candidate should initialize to be something reasonable. It will be a minimum from the initial. That's when we pretty much continue every time. So none of this is being updated. We want to return a random node, since that every node does not change the function result. We have to find the smallest one with respect to their index. So we do a minimum here. So the candidate has been promoted to the solution in the end after this for loop here. So let me quickly check, do I have problems? Okay, seems okay. Let's try run it. Nope. Collections default dict. Oh, sorry, it's not 0. It's int. Or I could do lambda 0, right? Yeah, this would do. Okay. Okay, so this is the union find solution to this question 924. Yeah, the description is pretty long and I guess all it takes is to draw some pictures to enumerate over a couple of scenarios and figure out what we do want to remove. What kind of situation we want to remove that node from initial, and how do we compare if there are sort of like a ties. Yeah, so that's it for today.